Alright, here's a quick question. What operating system are you running right now? Is it Windows, Mac, maybe even Linux? Or maybe you're one of those people dual booting Arch and pretending it's not your entire personality. Respect, but also please get therapy. Here's the thing though. Every single one of you, Windows, Mac, Linux, and even the guy on Chrome OS who's been quiet this whole time, you're all using something that took decades of people screaming at hardware to figure out. And in this video, we're going to understand why operating systems exist and how they actually work at a fundamental level. And hopefully by the end of this, you'll look at your computer and go, oh, so that's what's been happening under the hood all this time. This is the first video in a series where my goal is not to go into rigorous depth, but to build an initial intuition that kind of provides a sneak peek into the lecture slides and the textbook, both of which I'll be following closely. So let's get right into it. Okay, so let's start from absolute zero. Why do we even need an operating system? Here's the real answer, and it's almost disappointingly simple. An operating system is just a middle layer between you and the hardware. That's it. You, a human who wants to open Chrome and watch YouTube, and the hardware, which is a bunch of silicon that only understands ones and zeros. You two don't speak the same language, so the OS is kind of like a translator. It does a lot more than just translating, but we'll get into that later. If there is a bit of software somewhere that's sandwiched between a user and some hardware to make life simple, you can call that an operating system. It's really not that deep at its core. And if you break down the phrase into two words, you'll realize that they don't really mean anything by themselves either. And honestly, if you really zoom out, the concept of an OS is everywhere. Think about a light switch. You flip it and the light turns on. You didn't have to think about voltage regulators or circuit resistance. The switch is your interface. And now imagine you wrote a tiny piece of software that sits between the user and an LED. It reads a button press, sends a signal to the LED. Congratulations, you've basically written a baby operating system. The idea is just this. Give the user a clean, simple way to interact with hardware without the user needing to know all the ugly details underneath it. But let's be so for real. Hardware isn't just one LED. It's a CPU, a RAM, a disk, a keyboard, a display, a network card, and so much more. And you have multiple programs all wanting to use these resources at the same time. Maybe Chrome wants the CPU, or maybe Spotify wants it. Maybe your IDE wants the CPU too. Perhaps Cloud Code is just sitting on the side burning your tokens away as it builds you a multi-million-dollar startup while making no mistakes. That's a lot. So now the operating system isn't just a mere translator. It's also having to act as a manager. Your computer only has a finite amount of resources. And so the operating system has to decide who gets what, when, and for how long, without everything crashing. So to sum it up, an operating system exists because A. Humans don't want to talk to hardware directly. God knows the microprocessors course was enough fun for a lifetime. And B. When you have multiple programs competing for limited resources, somebody has to play referee. And that someone is the OS. Now, here's some context that actually matters. Computers didn't always have operating systems. So let's speedrun through some history. Back in the 1940s and 50s, computers were the size of entire rooms. And you didn't run a program the way you do now. You physically wired the instructions in, or you fed punch cards into the machine. One job at a time. You'd submit your stack of cards, go get a coffee, come back, and hope it didn't crash in an error. There was no OS. You were the OS. You were manually loading programs, managing memory, and handling I/O, the whole shebang. Then in the late 50s and 60s, people realized, hey, this is incredibly inefficient. The CPU is just sitting idle while waiting for I/O. So what if we loaded multiple jobs into memory and let the CPU switch between them? This was the birth of batch processing and eventually multi-programming. And that required software to manage which job runs when. And there you have it, early operating systems. Then the 70s roll around and Unix shows up. It was built at Bell Labs by guys like Ken Thompson and Dennis Ritchie, which already sounds like the kind of duo that either invents something legendary or forgets to document everything. Thankfully for us, it's the former. They basically wanted a simple, clean system. So naturally, they created something that half the tech industry is still trying to understand properly today. Their philosophy was do one thing and do it well, which sounds nice until you realize you have 15 tiny commands that each do a microscopic task, and now you have to combine them like Lego pieces at 2 a.m. in the night. So Linux is basically Unix child who read all the textbooks and then said, yeah, I can do that too, but open source, I guess. As for Mac, that's just Unix wearing a really expensive outfit and pretending it's not the same underneath, which explains why you can run Unix commands on a Mac terminal. And Windows took a slightly different path. They started with MS-DOS, did their own thing for a while, and then eventually they were like, okay fine, maybe structure isn't that bad of an idea. But the funny part is, no matter what you use today, you're still dealing with ideas that came out of Bell Labs in the 70s. The point is, every OS feature you take for granted today, which is multitasking, file systems, memory protection, each one of these was invented because someone somewhere had a real problem that needed solving. OSs didn't just fall from the sky or come pre-built. They were iterated into existence by decades of engineers yelling that there has to be a better way. Now, while we are on history, let me touch on something you'll hear about a lot. RISC versus CISC. This is about the CPU's instruction set, the actual commands that the processor understands. CISC stands for Complex Instruction Set Computer. Think x86, which is what most Intel and AMD chips use. The philosophy here is, give the CPU lots of complex instructions. One instruction might do a memory load, an add, and a store, all of it in one step. Fewer instructions per program, but each instruction is heavy duty. RISC stands for Reduced Instruction Set Computer. Think ARM, which is in your phone and now in Apple's M series chips. The philosophy here is opposite. Keep each instruction dead simple, but one instruction does just one thing. You need more instructions obviously per program, but each one executes super fast and often in one single clock cycle. Neither is objectively better, but they're just different design philosophies. RISC tends to be more power efficient, which is why your phone doesn't chug through the battery the way that a gaming PC does. CISC, however, has historically dominated desktops and servers, but the lines are blurring today. Modern x86 chips internally break complex instructions into micro-ops that look a lot like RISC, and ARM is moving into laptops and servers, so it's kind of converging. But knowing the distinction matters because it affects how the OS interacts with hardware at the lowest level. In the next video, we'll go over things like the fetch, decode, execute cycle, process virtualization, and defining what a process even is, and how so many of them run on a CPU at the same time.